Hi, my name is Richard. Today, our discussion will be on solving Valley View University end of semester examination. That's 2020-2021 academic year on Calculus 2. So please come along with me. So as you can see, this Valley View University School of Education, Department of Mathematics and Science Education, end of semester 2020-2021 examination. So the exam is divided into two. It lasts for 3 hours. The first part is part A. They say students are supposed to answer all questions in this part. And there are two questions there carrying 40 marks. Each is 10 marks. The second part
How many questions?
so the second part have 5 questions, and students are to answer 3 questions from this part. So today, before the video end, we'll solve all the questions in this examination. So come along. So we start things off with the first section. That's question 1a. So we should solve the differential equation dy over dx minus y tan x is equal to sin x using integrating factor. So this question is on linear first order ordinary differential equation. And to solve linear first order ordinary differential equations, you need an integrating factor. So what's that integrating factor? The integrating factor u of x is given as the integral of p of x dx. What is this p of x? The p of x is equal to the coefficient of this y here. So the coefficient there is negative tan x. So we integrate that. So our u of x will be equal to the integral of negative tan x dx. So we can bring the negative out. So have negative the integral of tan x dx. Now when we integrate tan x, remember, we'll get negative ln cos x. So when we simplify this further, we'll get exponent. The negative was first, so we have ln cos x. So anytime the exponential function meet the ln function, the answer is nothing but the function here. So this is equal to cos x. So we can say our integrating factor u of x is equal to cos x. Now if you find the integrating factor, what next? You multiply the integrating factor through your differential equation. So since we found our integrating factor, we multiply it through. So we get cos x dy over dx minus y tan x cos x equal to sin x cos x. We can polish this further to get cos x dy over dx minus, I can change my tan to sin x over cos x equal to sin x cos x. So we can simplify further. I'll get cos x dy over dx minus, this will divide us. We'll get y, negative y sin x is equal to sin x cos x. Now look at this. We said that after we multiply the integrating factor through the differential equation, the left-hand side of the equation will be nothing but the product differentiation of the integrating factor and the dependent variable. So we said this will be y cos x, the differential of that, and it should be equal to sin x cos x. Why is this so? Look at it. When we want to differentiate this, we have to use implicit differentiation, and which involve product rule. So we keep cos x and differentiate y, we get dy over dx. Then plus, So plus, we'll now keep our y and differentiate cos s. Remember, when we differentiate cos s, we'll get negative sin x. That's how come this place become negative. So we get negative y sin s and it's equal to sin s cos s. So we are right to say that this side is the product differentiation of the dependent variable and the what? And the integrating factor. So after we get this, the next thing is that we integrate both sides. So the next thing is that we integrate both sides. So sir, we have integral y cos s, the differential of that will be equal to the integral sin x cos x dx. Now, anytime you integrate the differential of a function, you get a function back. Or we can say this differential can just do away with the integral. So we have y cos s is equal to the integral of sin x cos s ds. Now, how do we integrate sin x cos s ds? So let u to be equal to sin x. Now we differentiate du over ds will be equal to cos s. I'll make du the subject. My du will be equal to cos x dx. So in place of cos x ds, I'll substitute du. In place of sin x, I'll substitute u. So the integral of that will just be nothing but the integral of u du. The integral of u, remember, will be half u squared then plus our constant of integration. What's u? U is sin x, so we substitute back. We have half sin square x plus c. So we can say the integral of sin x cos s is half sin square s plus c. So in substituting, we have y cos s is equal to half sin square s plus c. We can re-polish this to be y cos s is equal to sin square s over 2 plus c. Then we say this becomes the general solution to this our linear first order differential equation. I hope you get that. The next thing is we solve the B aspect of the question 1. So the first question we solve, the A aspect worth 10 marks. Then the B aspect also 10 marks. This is 7 and that's 3 marks. So now let's solve this. Find the first derivative of the following functions. I, y equal to 1 plus arc tan x over 2 minus 3 arc tan x. So this is on differentiation of inverse cyclic functions. So, arc tan x is the same as the inverse of tan. And remember, when we differentiate tan, the inverse of tan, we get 1 over 1 plus s squared. So that's that. So what do we use to differentiate it? We use quotient rule to differentiate that. So we let u to be equal to 1 plus arc tan x. Then we let v to be equal to 2 minus 3 arc tan x. Now we find du over there. So our du over dx will be equal to, we differentiate this 10 by 10. When we differentiate 1 is 0. The differential of arc tan x, the inverse of tan, will be 1 all over 1 plus x squared. We differentiate these two, dv over ds. When we differentiate 2 is 0, we differentiate d, we get minus 3 times the differential of arc tan, that 1 over 1 plus x squared. When we polish this, we get negative 3 over 1 plus x squared. So from quotient rule, our dy over dx will be equal to v du over dx minus u dv over dx all over v squared. So we can say this is equal to, what's our v? The v is 2 minus 3 arc tan x. Then du over ds is 1 over. So times 1 over 1 plus s squared. Then minus u. U is 1 plus 1 plus arctan x, 1 plus arctan x, then times our dv over ds. dv over ds is negative 3 over 1 plus x squared. Then all over v squared, and the v is 2 minus 3 arctan x all squared. So I'll polish this further. This will multiply that. So we'll get 2 minus 3 arctan x all over 1 plus x squared. Then look at the minus here multiply. So we can say plus 3 bracket 1 plus arctan x over 1 plus x squared over 2 minus 3 arctan x all squared. So we can expand this bracket. So we'll get 2 minus 3 arctan x plus this multiply this 3. Then this times this will be plus 3 arctan x. Because they have the same denominator, we can say all over 1 plus x squared, then over 2 minus 3 arctan x all squared. So simplify the top. See, minus 3 arctan x plus 3 arctan x will be 0. Then 2 plus 3 will be 5. So we have 5 over 1 plus x squared. Because this one is divided, we can reciprocate and multiply. So we say 1 all over 2 minus 3 arctan x all squared. So I'll polish this further. We'll say that dy over dx is equal to 5 over 1 plus x squared, then times 2 minus 3 arctan x all squared. Then this becomes our first derivative of this function. I hope you get that. The next one is this. So the next one is the first derivative of this function. This is an exponential function. And remember, the differentiation of exponential functions, we'll differentiate the exponent and use it to multiply the function. So we are going to find the differential of tan x squared plus 1. So how do we differentiate tan x squared plus 1? We have to use chain rule to differentiate that. So let's say we let u to be equal to tan x squared plus 1. I can do it straightforward, but for the sake of some of us, let's go like this. Then we let a to be equal to x squared plus 1. So our dA over dx will be equal to 2x. Now, if a is equal to that, we can say u is equal to tan a. In place of x squared plus 1, we substitute a. So our du over dA, remember the differentiation of tan is sec square a. Now we use what is known as chain rule. So our du, we want to find du over dx. So du over dx will be equal to dA over dx times du over dA. Look at the du, we divide the du, we have dA, we divide dA, we have du over dx back. So our du over dx is 2x times, what's our du over dA? That's sec square a. So we replace that. A is what? A is equal to x squared plus 1. So we replace that. We have x squared plus 1. Then we can say the integration of the differentiation of tan x squared plus 1 is 2x sec square x squared plus 1. So we say in exponential functions, we differentiate the exponent and use it to multiply the function. That's the differentiation. On differentiate different exponents, we get 2x sec square s squared plus 1. Then we can say that our dy over dx is equal to the difference 2s z squared s squared plus 1. Then we repeat the function e exponent tan s squared plus 1. Then this becomes the first derivative of this function. So that ends the question 1. We'll go to the question 2. So this is the second question. They say we should find dy over dx if y is equal to tan inverse of sin x, y is equal to cos the square root of x, then y is equal to tan x plus s squared cosec x. This is what 7 mark, this is 7 mark, and this 6 marks. So how do we do that? So this involves the derivative of inverse hyperbolic functions. So we use chain rule to do that. So let u to be equal to sin x. Our upon we find du over dx. Du over dx, remember when we differentiate sin x, we get cos x. Then our y will be equal to, in place of sin x, we substitute u. So we have y equal to tan inverse of u. Then we differentiate that. Our dy over du. Remember the differentiation of inverse hyperbolic. Please check out my videos on differentiation of inverse hyperbolic functions. This will just be 1 over 1 minus u squared. So now, our dy over dx from chain rule will be equal to du over dx times dy over du. So that the du divided du, have dy over dx back. What's our du over dx? That's cos x. So we have cos x times our dy over du is 1 over 1 minus u squared. On polish this further, we'll have cos x all over 1 minus u squared. However, we know u to be sin x, so we substitute back. So we have dy over dx is equal to cos x over 1 minus sin square x. That's in place of u, we substitute sin x. Remember that sin square s plus cos square s is equal to 1. So we can say cos square s is equal to 1 minus sin square x. So in place of 1 minus sin square s, we can substitute cos square s. So we can say this place, we substitute cos square s. So this will be equal to cos x over cos square x. So cos x over cos square x will be 1 over cos x. And remember, 1 over cos x is what? Is sec x. So we can say our dy over dx is equal to sec x. I hope you get that. The next one is this. So the next one is, if y is equal to cos root of x, we should find dy over dx. So we are going to use chain rule again. We let u to be equal to root of x. And this is the same as s exponent half. We differentiate this, du over dx will be equal to half x. So we subtract 1, we get negative half. On polish this further, we get 1 over 2 s exponent half using the idea of indices. So this can be 1 over 2 root x. So we can say that our y will be equal to, in place of root x, we substitute u. So we have cos u. Then we find dy over du. Dy over du will be equal to, remember the differentiation of hyperbolic function. The differentiation of cos is shin u. So product rule, chain rule say that dy over dx will be equal to du over dx times dy over du. So what's our du over dx? Du over dx is how 1 over 2 root x times our dy over du is shin u. On polish this further, we'll get shin u over 2 root x. So our u, remember u is equal to the square root of x. So we just replace it. So we have shin root x over 2 root x. Then that's become the value of dy over dx. So the next question is that y is equal to tan x plus s squared cosec x. We should find dy over dx. So we differentiate this 10 by 10. So we say our dy over dx will be equal to the differential of tan x plus the differential of x squared cosec x. So our dy over dx will be equal to, remember I want to differentiate tan x, it will be sec square x. So we have sec square x, then plus, how do we differentiate this? We use product. We keep one, differentiate the other. So I'm keeping cosec x and differentiate s square. I'll get 2x cosec x plus. Now I'll keep x square and differentiate cosec s. Remember, when I differentiate cosec s, I'll get negative cosec x cos x. Please check out my videos on the differentiation involving hyperbolic functions on YouTube. So we have dy over dx is equal to sec square x plus 2s cosec x, and this will be minus s squared cosec s cos s. Then this becomes our derivative of the dy over dx of this function. I hope you get that. So we are going to the section B, where we have 5 questions and you are supposed to answer 3 out of it. So the first question A, we say evaluate the integral of the square root of 9 minus s squared over x squared dx using the substitution s is equal to 3 sine u. So you are asked to use a substitution. In place of x, you substitute 3 sine u, then you integrate. So we can say that our x over 3, when I divide both sides by 3, is equal to sine u, and my u will be equal to sine inverse of x over 3. Please get that, very, very necessary. So now let's go on. So our integral of the square root of 9 minus s squared over s squared du, s squared dx, we are going to substitute the necessary thing. So everything will be changed into u. So remember, s is equal to 3 sine u. So we need to find the u out of this. So we have with dx over du, when we differentiate this, we get 3 cos u. Then we can say our dx is equal to 3 cos u du. Very, very necessary. So in place of dx, we substitute 3 cos u du. Then in place of x, we substitute 3 sine u. So what do we have? We'll have the integral of the square root of 9 minus, there is x here, so we'll have 3 sine u all square over 3 sine u all square. Then my ds is what? 3 cos u du. So if I simplify further, I'll get the square root of 9 minus, when I square this, I'll get 9 sine square u over 9 sine square u times 3 cos u du. So this will further be simplified. See, 9 is common, we can pull it out. So I have the square root of 9 out, 1 minus sine square u over 9 sine square u times 3 cos u du. So if I find the square root of 9, I'll get 3. So I'll get 3, the integral of 3, 1 minus sine square u, that's the square root of that, over 9 sine square u 3 cos u du. This 3 can multiply that 3, we'll get 9. So we'll have the integral 9, the square root of 1 minus sine square u over 9 sine square u, then cos u du. So this 9 will divide that 9. What's left? We will be left with the square root of 1 minus sine square u over sine square u cos u du. So this is our 13 marks question. You should get it to be long. So let's get identity for the square root of 1 minus sine square u. Remember, sine square u, okay, plus cos square u will be equal to 1 from our trig identities. So we can say that cos square u will be equal to 1 minus sine square u. The first one you should know. Also, when we find the square root of both sides, cos u will be equal to the square root of 1 minus sine square u. So in place of the square root of 1 minus sine square u, we can substitute cos u. So we can say this is integral of cos u over sine square u times cos u du. So when cos u multiply cos u, we'll get cos square u over sine square u du. Remember, cos square u is the same as 1 minus sine square u, so we can replace it again. So we said that will be equal to 1 minus sine square u all over sine square u du. So you can split this and have 1 over sine square u minus sine square u over sine square u du. So when we polish this further, remember, we'll get, look at it, 1 over sine is cosec. So we can say that will be cosec square u minus sine square u divided by sine square u is 1 du. So we need to know the integral of cosec square u. Remember, when we differentiate cot x, okay, the differential of cot x dx, remember it will be equal to negative cosec square x, if you remember very well. Please check out my video on differentiation of trigonometric functions. So we can say that the integral of negative cosec square will be cot x. So we'll remove the negative here when we integrate. Okay, so we can, multiply both sides by negative. So we can say that the integral of this will be negative cot x. The integral of just that. When we multiply both sides by negative. So the integral of cosec square x is negative cot x, if you understand. So the integral of cosec square u is negative cot u. So we say the integral of cosec square u will be equal to negative cot u. And the integral of negative 1 will be minus u. Then plus our constant of integrating. Now, remember u, look at it, is equal to sine inverse of x over 3. So we can substitute back. So we get negative cot, in place of u, we'll substitute sine inverse of x over 3 minus, this will be sine inverse of x over 3, then plus our constant of integration. So we can conclude that our integral of the square root of 9 minus s squared all over s squared will be equal to negative, I'll factor out negative. I'll get cot sine inverse of x over 3 plus sine inverse of x over 3. Okay? Then plus our constant of integration. I hope you get this. So the B aspect of question 3 says we should evaluate the integral of 1 over x ln x dx. This is for 7 marks. So how do we do that? So we say, look at it. When we differentiate ln x, we'll get 1 over x. So first, we can rewrite this question as 1 over ln x, 1 over x dx. See, when we multiply this again, we'll get this back. Now we let our u to be equal to ln x. So du over ds. Remember, when we differentiate ln x, we get 1 over x. So our du will be equal to 1 over x dx. So in place of ln x, we substitute u. And in place of 1 over x dx, we substitute du. So I have the integral of 1 over u, then 1 over x ds is just nothing but du. Now when we integrate this, 1 over u is just ln u, and plus our constant of integration. What's our u? U is ln x. So we can say when we replace, we'll get ln of ln x plus c. Then we can conclude that the integral of 1 over x ln x is equal to ln x plus c. So please remember to subscribe to my YouTube channel and click on the notification bell so that when I post most of this, you'll be the first to receive it. We'll end it here today. Check out my videos on part 2 of this, where we'll solve the number 4 to number 7 of the Calculus 2 Value View examination.